Have any difficulties, you have challenges, bring it to the class. We are going to see. But don't just bring it. You have to do something down. If there is no question, we move on to another topic under energy 1, and that is heat transfer. We want to quickly look at the heat transfer. The other class on Monday, I told you that we are going to heat capacity and specific capacity. Why do I want to do that is because in that area you have calculations, and that is what poses more problem to some of you. But I want to quickly touch this one that has no calculation too, so that we know that they are also important. Yes, I can see your hands up.
Is ice more denser than water?
Now that question is for us. Can we hear him very well? The question is ice block denser than water? Am I right? Is that the question? Who answered that? Yes, the question is for the class and not for me only. Or let me simply say I don't know. I don't want yes. You want to contribute, raise up your hand, we listen to you. Don't cross yes. You give us your own opinion. Yes, let's hear from you.
No, sir.
Say no.
Why? Because ice block at 0 degrees Celsius begins to expand. At below 0 and below 4 degrees Celsius begin to expand, and they don't change in volume. While ordinary water and ice block, they attain the same volume. In ice block, when it is freezed, the water expands and not increase in volume.
Okay, please clap for me. I know somebody that voluntarily wants to say something. Ice is not denser than water, which is very correct. But he was trying to put some reason why he says so. Not all what he said is not all like that, but the no is no. Somebody else put up his hand. Let's hear from him before we proceed. Yes? You withdraw. Girl, you have not been talking. All these things you've done it in SS1. They are not new to you. You should not stay as if you have not heard this thing. This should be a revision class. I'll quickly move on to the one you have not done. Let's start by saying ice block. What is the position when you drop ice block into the water? Where does ice block stay? You ask the question, I ask you. Where do you think the ice block will stay? It floats on the surface of. So what do you now call ice block? Floating.
Yeah, floating ice block.
It is floating object. And if object is floating, floating on the surface of liquid, it means that object is not denser than the liquid the object is floating on. Do you understand? That is from layman observation, which is still scientific. You cannot be floating on a liquid and claim to be denser than that liquid. You cannot carry a load heavier than you, can you? So if ice block floats on the surface of liquid, it means the density of ice block is smaller than the density of the liquid. And what makes the density of ice smaller than that of liquid is what he was trying to give to us, which we already said before. When you are now cooling, freezing, the volume of ice increases. The mass of water does not increase. It will now make the density of the ice to be smaller than density of water, and that will now enable the ice to be float. That is one angle. Another angle is upthrust in liquid will be equal to the mass of the ice block. The upthrust is a force that is acting upward in the fluid, equal to the mass of the ice block. So the octopus is able to suspend the block on the surface of the, not at least 1/3 of the ice block will be above. Am I communicating? Do you understand now? Ice is not denser than water. For if it is denser than water, it will sink. So that is that. Let's go straight to what we want to talk about. I said the first class we talked about heat. And we said heat is a form of energy that flows. Isn't it? From one point to... You still remember that? Good. Now we want to now talk of mode of flowing. How does heat move from one point to another in various states of matter? That's what heat transfer is. You already know that heat is a form of energy that flows from one point to another due to what? Temperature difference. Isn't it? Yes, how does heat flow from one point to another in solid matter? How does it flow from one point to another in fluid? That is, in liquid or gas. Then, can heat flow from one point to another in an empty space where there is no liquid, no gas, no solid? Can heat flow? That is what we want to briefly discuss in the next few minutes. And like I said earlier, under this aspect, there is no single calculation. They are like any other subject that all you need to do is state some technicality there. That's why I want to skip that before to move to heat capacity and specific capacity. But I will take my time to briefly discuss so that you will know that they are also important for all exams you have this year. That process is called conduction. So, to move from one point to another in solid, that process is called conduction. Am I communicating? Yes. Without the movement of the heated part, the heated part will not leave the part, it will not leave the portion. Yet the heat moves from that point to other parts of the solid material. Am I communicating? Is it a new thing? No. What property enable heat to flow from one point to another in the material? That property is called conductivity. What do I say? Conductivity. So, when we are talking about solid conducting, we have some solid are good conductor of heat, while some solid are poor conductors of heat. The solid that are good conductor, examples of that solid are metals. Metals are good conductors of heat. And we have liquid that can also conduct fast heat, and that is also mercury. But when we are talking about conduction of heat in solid, metals are good example you can cite. But the metals too has different conductivities, just like yourself as you are out here. There is nobody in this classroom cannot run. Or is there anybody that cannot run here? When there is fire on the mountain, everybody runs. Isn't it? Run be fast. Am I communicating? The rate at which you run differs. That is the same thing for the metals. Metals are good conductors of heat, but they have different conductivities. Some conduct faster than the other. We have simple experiments to show that metals have different conductivities. You have copper, you can have simple experiments to show, to test the conductivity of the metal, which you can also know. What do I want to plant or put in you is to know that metal has different conductivities, and the heat energy flows in the metal differently. The rate at which they flow are different. You have simple experiments to demonstrate that. You can pick 5 different metals, including, solid, including wood and plastic. So you now look for a bath, drill the holes. You have that simple demonstration in your textbook. You can have 5 different solid material. Then you put a bath, insert, you can drill holes at the side of the bath. Then pour hot water into this bath and insert this metal or the solid into the holes beside the bath. Now, before you do that, you must have put wax on each of the solid, maybe 5 pieces of solid. Put wax. Wax is like ori or butter. Use that to rub all the part of the rod and insert the rod in the hole beside the bath. Before you know, the wax will melt to different lengths in different metals. You have simple experiment demonstrated in your textbook. So if among the solid you use, wood is there, you notice that the wax will not even melt at all to any length in wood. Iron may melt to the middle, but virtually all the length of the copper will have gone, and you have various length of. I hope you understand what I'm making across. Yes, that shows that the rate at which it flows in different metal differs are not the same, and it implies they have different conductivities. Materials that do not conduct at all are called insulators. They are called insulators, and such insulators are used to make handles. When you are having your pressing iron at home, some part will be very hot, and that is what you use to press your cloth. The other one you hold to hold the iron is the wooden part, that's the insulating part that will not conduct heat. The same thing with cooking pots. We have application of this conduction in them. If you have to mention application of conduction, that's what we are talking about now. Cooking utensils has the metal and the wood, which is an insulating part, so that your hands, to remove the pot, it will not be so painful to your hand to remove the pot. So we have some liquid that are good conductors. Example is mercury I've mentioned. And we have liquid that are poor conductors of heat energy. They don't conduct heat energy. Water does not conduct. It's a poor conductors of heat. So, having known what the conduction is, I've mentioned few applications of conduction. You can also read this. We can talk about how does heat energy move from one point to another in fluid. When we say fluid, we mean liquid or gas. Can somebody tell me the process by which it flows from one point to another in fluid? What is the process? Yes. Convection. Please clap for him. Convection. Point to another in a fluid. You can open bracket and say liquid or gas. Also explain all this process using molecular kinetic theory to explain it. You will notice that, just like we said earlier, when the molecule is heated, the volume increases. And when the volume increases, the density becomes lighter. And so the heated molecule will be struggling to go up, while unheated molecule will now come down to replace. Once the unheated come down to replace the heated, by the time it gets heated too, it will also struggle up. So this will continue until water starts to boil. That movement is what we call conventional movement. The heated molecule leave the fire side and go to other part of the liquid. Unheated will come and replace it. And you have the arrow of the convection. What we are saying in essence is, if you have a container like this, you have a container and you have your liquid. You have fire here, you are heating. The molecule here, after being heated, will move up. Some other molecule will replace it. So you have a kind of this movement. Heated one will go up, then it continues like that. This is what we call conventional movement. It is through the heated molecule, heat energy is transferred from one point to another in fluid. You can talk about other conventions are, yes, let's quickly talk about the application of conventions before we leave that alone. We have natural application. What are the application of convention you know? They are not calculations, they are what you have done before. Yes, any some contribution. So many applications you can talk about. Yes. That's natural. Clap for her. Land and sea breeze. Yes. Any other? There are many things you can talk about. There are many. Lots of ventilation you have. Air conditioning of the home is part of it. Yes, somebody is saying something. The natural one is the one he mentioned. Land and sea breeze. Land and sea, yes. Yes, cooling of car engine. Processing of that, you have that. So, please and please, all this processing we are talking about, at least you should be able to mention not less than 2 applications. Go and put not less than 2 applications in mind for the conduction convention we talk about now. Breeze, he said land and breeze, 2 of them are put together, land and sea breeze. Let's briefly talk about the 2 of them and see what happened to the 2 so that we can save our time to move on to topic that require calculations that you can easily read and understand, and that is heat capacity and specific. By the time we finish the other mode or the other way the heat is transferred. So, land breeze. What do you understand by land breeze? Yes, you want to talk about during the night. How does it occur? How does it occur? Okay, because of time. Yes, you want to say something? During the daytime like this, both the land and the sea are heated. Both the land and sea are heated. Which of the 2 will be hotter during the daytime? Why? Why do you think land will be hotter? Yes.
Because land has a greater heat capacity than lesser heat capacity than water.
Has lesser capacity than water. I don't want to use the term I've not taught you, but you have brought in capacity now. Now, obviously, whether you have no heat capacity or not, everybody knows that during the around 1, 2 o'clock, 1, 2, 3, the sun is very, very bright, and the land will be. If you remove sandal from your legs or your shoe and you march, you notice that even the sand will be hotter. The sand will burn your feet. You will feel the heat. Isn't it? Then if you go to nearby river, you enter the river, the water will not be as hot as the land you march. Isn't that true? Oh yeah. Look at the land hotter. It raises the temperature of land higher than that of the sea. And what happened when that happened is that the heated water vapor from the land, the heated vapor, the water that is turned to vapor from the land goes up. You know, the land is hot now. So, and the water is inside the land before when rain falls into the water. So the water will be evaporated. Hot vapor from the land will start going up. Am I communicating?
Yes, sir.
Then the cool air from the sea replaces the hot vapor going up from the surface of the land. What cools that one down is what we refer to as sea breeze. It is the breeze comes from the sea now to replace the hot one that is going up from the land. And that takes place during the daytime. During the daytime, land is hotter than the sea. Are you lost? Do you understand what we are saying? The hot land, water vapor from the land goes up. Then cooled air from the sea blows to replace the cool one, the hot one that is going up. And that is what will continue. What we are trying to say, from vapor going up like this, going up, going up, going up, to form the cloud. Later, after some time, it comes to form. So the cool air from the sea, you have sea here. This is the land. So you have the land, the breeze, cool breeze. This is cool breeze. This is hot, going up like this. This movement of the heated air up here, cool one replaces it, is what we call sea breeze. This is what is cooling this one down, and that's why we refer to it as sea breeze, which occur during the day. It as land can be heated and temperature rises up during the day faster. So the land can cool down faster than the sea. Am I communicating? So in the night, the land will be cooler than the sea. So it means rivers or what happened during the day will now take place in the night, because the water is a bit warmer than the land now. So we expect hot air or hot breeze to go above the sea, while the cooler one replaces it from the land. And that is what we refer to as land breeze, which take place in the night. Are you lost?
Yes, sir.
So what causes land to change its temperature faster is what it's trying to tell us. It has to do with the specific capacity of the land and that of water. But you get to know that by the time we treat the next topic. But even if you don't mention, you don't explain it using capacity or whatever, what I've just said is simple enough to get your mark. You need not to cram anything. What cools is giving name to what you are giving. Land will cool sea, and that occurs in the night. During the day, sea will cool the land. Just have that simple, code that in your mind. Then you know the difference between land and sea breeze when it occurs. Am I communicating? Yes. So you need not less than 2 to 3 authority before you can settle your mind. Your textbook, of course. You can have 2, 3 textbooks. That's each of textbook is an authority on its own. Your teacher is another authority. You yourself. So when you have 4 authority and 3 of them pick the same, you should know majority carry the vote. That's the way we answer questions that are not calculation, theory questions. I hope I'm communicating. Yes. All these are not calculation. It's just a matter of read and pick, and you are all doing English. Comprehension. Isn't it? Yes. Okay. So that's all about the convention. The last one is that's a process by which heat energy flow from one point to another in a vacuum. What is the process? What's the name given to transferring of energy through a vacuum? Radiation. Radiation too is not different from other methods. or mode of transferring heat from one form to another. It is the process by which heat energy flows from one point to another in a vacuum. And of course, the radiation we are talking about is different from that of convection, because convection moves from the lower part to the up, heated up, heated up. But convection, radiation, of course, the heat from the sunlight, gets to the heart by process of radiation, and the sun is above, not below. Air conditioning. If you want to install your air conditioner at home, you don't install it below the room. You don't install it below the room because the cool air that will blow will be heavier than the warmer one. And the heavier one cannot struggle itself up. And that's why they put air conditioner almost at the top of the house, the office. It may be above the window or very close to the ceiling. It is when you have your AC very close to the ceiling, your room will properly cool down, because as the air conditioner blows the air, the air above will be cooler than the one below. And as soon as they get cooler, they become heavier. The heavy molecule will sink. The lower one, which is lighter, will go up to go and get their own share of cooling. By the time that one is also cool, it comes down. The cool air is heavier than the warm one, unheated one. The cool air is heavier than the warm air. So the cool air above will always sink down, and the warm will go up. That's why the AC is still part of conventional. What I'm giving to you is application of conventional. The kettle, electric kettle, you have the heater below. That is also conventional. Am I communicating? All that has to do with application of convention. Then, to let you know that radiation is quite different from convention. That's why we say the sun is above. The sun heats. The energy from the sun gets to Earth by radiation. So it has to do with the energy coming down to the Earth. Or you put hot body, and hot body radiates, give out radiation. Am I communicating? Yes. We have application of this in thermoflask. And what do they do in thermoflask? All the means of transferring heat are put into operation in thermoflask. You prevent heat loss by evaporation. You prevent heat loss by conduction in thermoflask. You prevent heat loss by convection, and of course heat loss by radiation. Now I will quickly talk about good absorbers of heat energy and good emitter, still under the application. Good absorber of radiation and good emitter of the radiation. But before I say that, let me ask you, can you give example of good absorber of heat radiation, and give us the reason why you give us that example? I want somebody that has not talked before. Do you have something to say? You can sit and talk loud.
A black coat.
A black coat. A black coat. A black coat. In other words, black. Black, whether coat or not, black color absorbed radiation. That is radiant energy. Heat energy is absorbed by black. And that is why it is not advisable during the dry season like this to wear black. Either black coat or black car or anything black, because black color and dull surfaces. Black and dull surfaces absorb heat energy. They are good absorbers. They have simple experiments to demonstrate this, but because of the limited time, we cannot go into demonstration of all the surfaces that absorb or emit black heat energy, so to say. So we have good absorbers of heat energy, like he said, is black. Any black object absorbed. Then dull, communicating. Likewise, when you are talking of good absorber, they are also good emitter. That means what gives out heat energy. And this you can demonstrate at home, but you may not have that equipment. I may not ask you to go and do it. If you take tin, the milk tin, this liquid milk, you open the cover, and you paint the house black. You can pour hot water into that hot tin. I mean the tin that you coated black, pour hot water there. Take another tin, remove the wrapper. You know the surface is shiny, silver in color. Pour water. Water of the same temperature. Now you notice that the one in black tin will get cooler faster than the one in shiny surface. What does that mean? That simply means that just as you have black as good absorber, it's also good emitter. It emits heat energy faster than the shiny surface. So if in the objective you are given some surfaces, which of the following is a good emitter of heat energy? So you should know. In summary, what we are saying in essence is black or dull surfaces. Black, dull, rough. They are good absorber and emitters of heat energy. But shiny surface emits heat energy. And that's why it is recently you are seeing roofing sheet having various colors. In the past, our roofing sheet, aluminum sheet, is always silver, shiny, isn't it? The silver will reflect the heat energy. Hardly you will see a roofing sheet coated black, because if you coat it black, it means the heat energy from the sun will be absorbed and give to you inside. So it's better to have a shiny surface so that the heat energy will be reflected. It will not be absorbed and give to you inside. I hope that is cleared. So it is important to know how heat is transferred from one point to another in solid, in liquid, and in gas. When we say liquid and gas, the two of them are fluid. So, but you can also transfer heat energy through vacuum. You already seen it. I will see the application of this in thermoflask. The food flask you are carrying about also put all these things into operation. So far, so good. I am going to give some questions on Monday. I want to, you know my usual method. What is it? You will go back between now and Monday. Each of you will set 40 objective questions. 40 objective questions under expansivity. Expansion, so to say. Heat, transfer, expansion. You must not quote the question from the past question. You must not quote question from the textbook. Read and form your own question, 40 objective, and produce the answer separately. Last class, I was not able to do what I want to do because some of you put the answer and the question together. So this time around, nobody will claim that I didn't know that we have to separate it. You are going to set 40 objective questions on the topic, and it must not be past questions. You must not go from WAEC, you must not go from Ostezo. You read and form that. Then you now also form 5 theory questions that will also be answered, and bring them to the class on Monday. Is that taken?
Yes, sir.
Any questions on that? Yes, remain. What you actually want to do, which involve calculation, is heat capacity and specific heat capacity. But unfortunately, our time is gone today. We also talk about the sagging of telegraph wire as another application of expansion. We talk about bimetallic strips as an application, and lastly we talk about expansion in water. We talk about bimetallic strips application, which are: 1, we talk about the balance wheel of a clock. It affects it is applied in it, a clock or wristwatch. We also talk about bimetallic thermometer. And lastly, we also talk about thermostat, which is used in iron. We talk about anomalous expansion of water. How the volume of water is affected by the temperature, that between 0 and 4 degrees, the volume of water decreases. But from 4, the water behaves like any other liquid. That means the volume increases from 4, but decreases from 0 to 4. But density of water increases from 0 to 4 before it decreases like any other liquid. Please take note of all this. This will help you to form your own questions. And of course, your question will not be the same. So, we talk about heat transfer, process by which heat moves from one point to another in solid, in fluid, and in vacuum. Conduction, convection, and radiation, and their applications. Cleared?
Yes, sir.
Any questions? So, I will be waiting for your 40 objective questions on this topic and 5 essays on Monday. I need the attendance of today.